Welcome to another exciting edition of light modeling. We're getting ready to do Phong light shading here. My name is Nate Nessler. This is Hyperactive Studios, and this is for the CG programming series. Now, before we talked about a little bit about these math algorithms for lighting, and we looked at Lambert already, and we're going to be building on top of Lambert to create our Phong shader. And we have our R for a reflected ray here, and then we have our view ray here, and in between that is our shininess value here. Okay, an exponential value. So we're going to break this down again into 4 different shaders. We're going to have vertex without texture, vertex with texture, and then we're going to have our Phong without for our pixel shader without shading, without texturing. I mean, it has shading. And then with the texturing too. And so this is very cool and very powerful indeed. And you'll see the difference between vertex and pixel shader. It is significant, but there also is a big difference between performance here between the two. So, you know, it's all important. So, but you saw just then that layout, and then this is our actual Phong Vertex shader. So first thing you're going to want to do is bring up your copy and paste your code from your Lambert shader, but honestly we're going to be changing it quite a bit from what our Lambert shader is. So we're going to make use of some things that are optimized for doing these type of calculations. So, you know, once you start going past Lambert into these other shading methods, then you can start using these other some special functions and things of that nature in order to calculate your lighting faster and easier. And we're going to make use of those. Okay, so first go up here to create, then go to effect, and you're going to choose CGFX, and then you're going to give it a name. And you're going to choose empty here, and you're going to give it the name PhongVertex here. And then once you do that, you can say next here, and then say next again, finish it out, and then it'll create this new file. Paste in your code from your Lambert shader here. You may need to pause the video and go through this. But once you do that, you're ready to start off. Now, I did do things a little differently here, and I'm going to be adding more and more things that will make it a little nicer for end user, for the artist as we go through this, and more into each part here until we get the final things where it's really detailed and you have all kinds of power and control over a lot of stuff, but that gets to be pretty complicated. So we're going to keep things simple and just keep building up bit by bit here until you get into more and more complexity. Okay, and so with that said, we're going to be adding something we haven't been doing yet, and that is string UI widget here equals in quotes none, capital N there, semicolon, and then this is an opening less than sign, closing greater than sign with a semicolon at the end. And this is for our different parts here. So we have our worldview projection matrix here, and we also have our worldview projection, and that's really cool. So this sets up our worldview projection that we've been doing, but we have a colon here. Instead of ending it straight up with the semicolon here, we're actually adding this to the definition here as an annotation. Now, why does this matter? Because before, without this, it appeared up here in this setup here. Let me show you what I mean. Alright, so say I cut this out, and I go a semicolon here real quick. I'm just going to compile this particular one here. Notice you have worldview projection up here with a whole bunch of value that the artist cannot manipulate, and it's just extra information. It's something that the artist would have no idea what on earth that is, and so the best thing to do is just simply hide it from the artist. Well, in order to do that, what we're going to do is set this UI widget to none here on our annotation, and it takes care of that. And bam, it disappears. So I've done that for each one of these. So we have our world ITX, or world inverse transpose. Now, if you need to, you can go back and look at the videos for the matrices for inversing a matrix and how to do a transpose of a matrix. And that's essentially what we've done with the world coordinate system here. Here's just a straight up world coordinate system without being, as far as the matrix goes for that one, the matrix, and without it being inverse or transposed. Okay. And then we're going to make use of also the view IX here, or view inverse, inversing the view. So it's an inverse matrix, view inverse matrix, if you will. And again, I'm setting all these to none here, and it's this open less than sign, closing greater than sign, semicolon after each one of these. and that makes life a lot easier. So, here we have a float 4x4 matrix, of course, because it's a, it's a matrix that we're using to modify our point positions. So we have our world ITX here, F, lowercase f. You can name it anything you want, but please make it make sense. Colon, world inverse transpose. I just stick with this name because I've seen umpteen example shaders using this name, so I thought maybe it'd be nice to comply with what some other people have done, like NVIDIA, for instance. So I just went with the same naming conventions for some of the stuff. Float 4x4 here, world XF here, and then colon world, because it's a world matrix. And then we have a float 4x4 view IXF here, colon view inverse here, and that's because that's a view inverse matrix. Some other things here. In our instruct here, continuing on, here's the values we're going to be passing in. Now the only thing we're going to be passing in for our Vertex Shader, and this is important. Now you can actually see the highlight here on the surface, which is not what we got when we were dealing with the Lambert shader. And the key important thing about this is if I go in here, I can move my light here, and you'll notice that the specular is updating. The specular looks a little bit rough. That's because it's based on the vertices of the surface here. So the more vertices you have, the cleaner and smoother it looks. The fewer you have, the rougher it becomes. So you can see how, the more vertexes you have for this type of lighting method, the better result you get. So it's up to you, This computes, however, a lot faster than the pixel shader or fragment shader version of the Phong shader. So performance always wins, every day. It comes down to the end of it. Hey, you have to have 60 frames a second. So if you're on a device that has low power capabilities as far as computational setup or something like that, then you may have to go with a Vertex one, and this one goes way back on what you can do as far as the profiles here. So that's nice to know. And this is certainly a method that does go back, but if you want, you can also use the pixel shader methods. And on the newer games, the games coming out current generation and next generation, they use a lot of pixel shaders for doing their light models and methods, and it gives a lot better results, of course. Okay, so with that said, let's continue on. So we have our struct here. We're going to do a VS in here because this is your values are going to be coming into our Vertex Shader. That's right, VS here for Vertex Shader. And then we're going to have an open curly brace, and then we're going to say float 3 for our position. We're going to use a float 3 here, and we're going to use a float 4 for our position for our VS out. But float 3 position here, colon, all caps position, semicolon. That is a special name. Don't forget that. That's the position of our vertices. Don't forget our points of our models. So that's coming into our shader from our 3D app here. And then float 4 space normal here, colon, all caps normal, semicolon, close curly brace, semicolon. Alright, awesome. And that sets up our values that we're going to be passing into our shader here from our Vertex, for our Vertex shader, for our light model here, Phong. Okay, struct here. Struct VS out here, and VS is our Vertex shader for out. This is what we're sending out back to our 3D graphics program, and this is going to have our position of our points that has been modified by our worldview matrix here, so that we get this nice perspective distortion, and also the color, so that we also get this wonderful lighting effect that's occurred here from the Phong shader here. And this thing's really cool. And I'll get into some of the parameters here in just a bit, but this one's quite nice. But yeah, so we have our float 4 position here, colon, position, all caps here, semicolon, and then a float 4 color here, colon, color, semicolon, and it does need to be float 4 for both of these. It needs to be a homogeneous coordinates here for our position, and then we need our color as RGBA, absolutely required to be that way. So that's what you need to pass back when you send it back to the program. All right, so we have our tweakable parameters. Sorry. These are things that we can change for the artist. Alright, so we have our ambient light here. So I'm calling it, I'm doing a float 3 on it. I'm calling it global ambient. So if you remember right from your algorithm over here, not that one, but our global ambient one, this one right here, iAmbient. It's our global ambient value here, right? And here we're doing a open less than symbol, and then we're going to string UI name equals, and then in quotes ambient shadow close quotes, semicolon. Now you could call this ambient light if you like. That's fine. Ambient light intensity if you want. That would be a good one too. That would be something recognizable to the artist. Again, we want to keep this where it's really recognizable to the artist. To where they can easily make sense of what on earth it is that they're doing. Alright, in here we're going to do string UI widget equals color in quotes and then semicolon. Alright, and then we're going to have a closing greater than sign equals and then open curly brace here 0.07f. We don't want to do solid black because remember solid black is nearly impossible in reality. Alright, and then comma 0.07f comma 0.07f close curly brace semicolon. Alright, then let's go on to our next part. Remember Ka is going to be what our ambient artist controllable value. So here's our ambient shadow, our global or our ambient global ambient here, and you can see what happens when I turn this up. Oh yes, it does make it global ambient. Alright, and significantly changes that power here. Okay, so with that, let's have a look at our ambient color. And you can see the influence this has on our shader here. Very cool. I'm just going to turn down my ambient shadow again, because I like to have it down more. Alright, so it goes into darkness and recesses much faster with fast fall off from art. If you're familiar with lighting theory for art, this would be what called fast fall off, where it goes from light to shadow quickly. This would be more like flat, well this would be like flat lighting right here, where there's like no shadow, any angle practically, where the lights are just blowing out. Think of like a talk show host. They light them like crazy every direction so that no wrinkles will show up on their face. Alright, so that's that set up. Okay, and then our diffuse color, which is our main color for our shader. Ta-da! And with this, the artist can select any kind of color they want. Millions of colors actually with that. Okay, and then we have our specular color. And this is the color of our highlight here. Now I can go in here and change this too, and give it a really cool different look to the actual specular value itself. Of course, if I make it blue and I have solid blue for the other part. Pretty cool though. Pretty cool. Alright, and so that's controllable too. Alright. You can do this all kinds of different ways. You can have this driven by the light instead. In the area as a contribution of all the lights, that's totally fine. That'd be a great way to do it too. There's lots of ways to do this. So you could have it where it's not artistically controllable in the shader here for the specular color, but rather it be controllable by the lights or something like that nature, or a combination thereof, or whatever. There's lots of stuff you can do. Okay, so there's our Ka color, and so like I said earlier, open lesson sign here, and then we're going to do string UI widget equals color in quotes semicolon string UI name equals ambient color here, and then close the quotes semicolon, and then here I'm going to do a closing greater than sign equals open curly brace 0.8f comma 0.8f comma 0.8f comma 1.0f closing curly brace semicolon, and that colors our RGBA value with a light gray color, which is this gray here, almost this gray, close to that gray. Alright, again we already talked about the diffuse color, and this is what this KD is, so const float. Don't forget we're putting const here because why? We're doing uniforms, and that needs to be const too, matter of fact. Always leave this off from being const, I don't know why. Alright, it's just forgetful I guess. And there, it works fine. You can see it has absolutely no effect on the actual shader doing its job. However, this does have a massive impact on performance by putting that const right there, so that's important. Alright, so we have string here, and we have UI widget equals, and that's capital UIW in lowercase widget equals in quotes color, then semicolon, and then string UI name here, capital UI and then in name equals diffuse color. And if you remember right, this color here gives us what? It gives us the color swatch that pops up and lets the artist manipulate the color, And don't forget, what does the UI name do? Yes, it gives it the name here for the artist to see what on earth this control does. And it's not just a bunch of, controls here to manipulate stuff with no description of what on earth it is. Yeah, so this is make it easy for the artist, and of course artists will know what diffuse color is. Alright, so closing greater than sign equals open curly brace here, and we're going to do another mid-gray. Not another mid-gray, but another light gray here. So 0.8f, comma 0.8f, comma 0.8f, comma 1.0f. And then closing curly brace, semicolon, and that's going to give us our light gray color with no alpha transparency. Okay, moving on down to our specular. KS is our specular here. Now, if you're having a hard time remembering, how does he remember all these? Well, they're in the algorithm here. KA is our ambient here. KD was our diffuse. They're named over here. You can go back and look at this video, or you can read the descriptions here, and that's great. And KS is our specular for our artist controllable value here. The more and more you do this, the easier this comes, and you just get familiar with these different variables, as they're very standard, and this is used quite often in the industry. Okay. This is absolutely a must-know type thing. You have to know how to code Phong shaders and Lambert shaders and blend shaders and many other light model methods and other methods out there. Yeah, you have to. It's just part of the job. I mean, it's just something you absolutely have to know. So everybody wants this, wants lighting. Everybody wants real-time lighting. Real-time lighting's awesome, so everybody wants it. So you have to know it. Alright, so const here, float for KS here for our specular value. Now if you remember right, this is the highlight, the spotlight on this thing here. I colorized it earlier. Ta-da. So there it is, that's our KS. Okay, so our K is capital K, lowercase s, colon, color, right here. And then open less than sign, string UI widget equals, and then in quotes, color, ending quotes, semicolon, string UI name equals, in quotes here, specular color, ending quotes, semicolon here, and then closing greater than sign equals open curly brace. Remember, this is a curly brace, not parentheses. 0.8f. This is a common mistake. I know it's kind of weird having it there like that, but this is a common mistake, and this is probably a result of many headaches you might have already had when trying to type this up and debugging and finding your errors. But 0.8f here, comma 0.8f, comma 0.8f, comma 1.0 here, closing curly brace, semicolon, and that is going to give you your what? That's going to give you your specular color right here for artist controllable value. Awesome. And again, we definitely want color set here for this, because otherwise typing in these values to get your color is kind of difficult. So having an interface where the artist can easily interact with it to get the exact result what they want, is by moving around here, is so much faster. If you could imagine typing in these values one by one here, bit by bit, and then by process of elimination, it'd take you like 100 times longer, maybe 1,000 times longer in order to get the right color, where I can just sit here and grab and move on this color picker to get the exact color I need, exactly how I need to see what I'm doing here from an artistic standpoint. And that's exactly why you want to stick with things that's going to be easily great controls for the artist, where they can easily manipulate the stuff you program in order to get the look they're trying to do. Don't forget, they're doing art, so you have to make tools for the artist, and that's important. Very, very important, matter of fact. We also have our specular power. Now, specular power here is awesome. It actually creates the shininess of the surface here. Yeah. So the bigger this value is, the tighter the specularity is on the surface, or shall I say, the shinier the surface is. The shinier the surface becomes, the smaller the specular. Whereas the less shiny a surface becomes, then it's going to pick up more of the light because it's got more rough areas on the surface, and this is going to cause it to be more illuminated by the specular value, but you're not going to get what you would call a very shiny appearance to it. So that's important to note. I'm going to set this back around a I don't know, maybe I'll make it bigger. There you go. I'll hang around 11 for now. But that's our specular power. So this is, don't forget, in the algorithm, what is this? Well, this is your to the power of part here, the shininess here. Remember that? If I come over here and I click on this one right here, and I go over to our maximal cells here, and I say evaluate all cells, And if it loves me, it'll do it. It does. It loves me. Great. Good. And this will be the shininess value here to the power of. And basically we're doing to the power of r dot v here. But in our shader we're going to do r dot n instead of v. And it comes out correctly if you do it with the n instead of the v within the shader. It does not come out correctly if you do it with the v. But the v is used up in the calculation in the r, so it's not a problem. It comes out correctly. So it's still taking into consideration the v direction through the r operation by adding the two vectors. Okay, I'm calculating r, basically. It calculates faster that way. Okay, so with that said, oh yeah, and if you want to, you can check it out over here. And yes, we can see our shininess coefficient here, or shall I say shininess exponent. We go up to the exponent of the shininess, and that's what this little alpha here is. I think that's an alpha, yeah, Greek alpha. Alright, so from there, let's look at what we can do. Alright, so okay, here we are. So we have our specular power. And so we're saying float, because it is just a float, and we're going to call it spec power here for the name of it, colon specular power. Ooh, I don't like having that up there. I'm going to bring that back down so that it's nice and well formatted, so it's easy to follow and read. And then I always want to stick with a consistent format here, and this is easy to read. Also makes it easy to tell if you've missed one of these or not. It helps debug faster. Makes a good reason for doing good formatting. Okay, string here, UI widget, capital UIW here, lowercase widget part, and then equals to, in quotes, slider, and then close quotes, semicolon here. Float UI min equals 1.0, and why slider, of course, because this is a slider interface. Let's just get our slider type set up. So that makes sense. We're creating a slider, that's why you have to tell it to be a slider. Alright, so our UI min here, our minimum value here is going to be 1 on our slider. So you can see right here, 1.0 is our minimum value. Whereas our maximum value here is 128. And so you can see we can go up to a maximum of 128 here for our specular value. And at point where it reaches almost 128 here, beyond that you don't hardly see a difference perceptibly in the actual, shading here. When you drag this value back and forth beyond 128, you can't even hardly visually tell a difference. So that's the reason why we stop at 128, and it makes it easier for the artist to control this slider here if we don't have, like 10,000 in here when it's barely doing anything at all, Makes sense. This way the artist can control it easier for their specular value here. And again, it's all going back to making it easier for the artist. UI max equals 128.0 semicolon here, and then we're going to do another float. We're going to do UI step. Remember, we're going to do step value here. Right now we're doing 1.0. If you want, you could do like 0.1. That might be a nice step value, so you're not popping here. Currently it pops, slightly here, like so. But if you wanted, you could do, a smaller value and have like a point here. I probably wouldn't go below that because it's going to be harder to accurately put in a value by dragging it. Okay, so string UI name equals, in quotes, specular power here, in quotes, semicolon. And then we have a greater than sign here for closing our annotation here, and it equals 55.0 semicolon. Alright, great. So that's going to be its starting value right here. And of course the name is Specular Power, and it shows up as Specular Power. Alright, so moving on to our point lamp 0, or shall I say our light. Alright, so we're setting up our light, and we're doing our light position here first and foremost. So float 3 here, lamp 0 pose here, colon position. Now how did I get to this? I did Control J. Control J gives me my point light, and a number of other things you may need. But in particular, point light. Yep, world view projection, so on and so forth. All kinds of stuff you may need. It's great for just easily popping things out and then reassigning and renaming things appropriately to what you need. Alright, so we have here colon position, because it is a type position, because it's modifying its position value here in the light. And then we have an opening less than sign here for our annotation here, and then we have string space object This is a particular name. You do need to use this exact naming, spelling, everything. Equals and capitalization. It is case sensitive. In quotes here, point light 0 in quotes here, semicolon. And then string UI name equals lamp in quotes here, 0 position in quotes, semicolon. And then string space equals world in quotes here, and then semicolon. We're going to close our annotation with a greater than symbol, and then we're going to say equals, and then open curly brace here, negative 0.5 f, comma 2.0 f, and comma 1.25 f, closing curly brace here, semicolon. Now I want to point something out. That's the default location. However, when I create the light and put it in here, the light's going to be driving this value here. So check it out. When I move this light here, saying okay, whatever. Alright, see the position here? This position is based on where I move my light. You'll notice that the numbers completely changed from what they were a second ago. And again, they changed again. So it's getting the value from the actual light, and it's being driven artistically as a moving parameter here. So this is not something you have to hand enter. I have seen other people do this, where they set up their shaders where you have to hand enter the position of the light for the points, instead of being able to artistically manipulate and position a light. And needless to say, that is extremely difficult to get the right look to it. I've seen them with sliders and go, oh, we'll make it a little easier to add a slider to it. It's still a pain in the butt. You're still limited to the range of that slider. You're still, trying to get a precise value and position something suddenly becomes difficult, because as you move across the slider, suddenly that light starts jumping from place to place. You're like, okay, I need to get here near this space, and then next thing you know, the light's gone through the door if you barely move the slider. It's just a nightmare. So again, it comes down to making interfaces that are easy to use for the artist. It's important. And here we can just grab the light and automatically have it update the value. And that's ideal. That's definitely going to work a lot easier for the artist. It's hands-on, it's intuitive, it's straightforward, and it doesn't cause any headaches. So that's what we want. Good interface design. Okay. Float 3 here, lamp 0 position. Already went over this. Okay, so float 3 here, lamp 0 color. So this is going to be the color of a light. Colon specular. And we need to say specular here for our light. That's a special name here. Open less than sign for our annotation here, and then string space UI name equals in quotes lamp 0 color in quotes here. So that's going to be our name for our lamp color here. Now we're not going to adjust our color here. You're sitting going, well, I can't click it. It doesn't do anything. You're right, you can't. But if I go over to my light, check it out. Here's my light color. And it does influence my shader. Okay? So I've set it up to where the light actually does influence the shader quite a bit. So if I have colored light in here, it will colorize my model accordingly. No doubt about it. So very cool, very powerful, and really nice. So when someone sits there and adjusts the light, automatically it's going to affect my model, and I don't have to have someone then come back for the artist and tweak some other control on the shader here in order to make it look like the light's affecting this shader. Instead, I'm having the light drive the coloration here, and not just an intensity value for my lighting here on my model, and that's important. You definitely want to do that. That's makes life so much easier for the artist. Again, intuitive, just needs to be intuitive and make things tie together and work together very easily and very in a smart way to minimize complexity for the artist. And this is very straightforward and easy to use. So that's what you want to do. Alright, so we have our opening greater than sign, less than sign. And then we do, I already said, I don't know if I said, okay, string UI name equals, in quotes here, lamp 0 color, in quotes, semicolon here. And then we have our string object, capital O here, equals, and then in quotes here, point light 0, in quotes, semicolon. So it's our first light object here. And then string UI widget equals color here, in parentheses, in quotes, semicolon. And so this is going to be our color wheel value, which you can see here. And then we're going to have closing less than sign here equals curly brace 1.0f, comma 1.0f, comma 1.0f, closing curly brace, semicolon. So that means the light's going to start out as a default white, solid white light. And that's perfectly awesome and fine. And there's nothing wrong with that. And I recommend doing, white light. You do want to start off with white light. And the reason why is because you don't want someone playing with the shader thinking that the shader's too dark or too, or off on some color. Say you set your light to the default to red, and then the artist sitting there manipulating their shader or whatnot, and the next thing you know, they're sitting there compensating for the red light, and they just didn't realize their light was red when it was first created. Not to mention it's going to be a hassle because they're going to have to constantly go back and set that thing to white so they can accurately create their shading before they start colorizing the light, and have a lighting artist come in and adjust the light for everything. But the material artist is going to have it to where they get the look they want without the light, affecting it for color before you have a color applied to it from the light. So it's really key and important aspect here in order to have the the light be white when it starts out. That's very important. So always leave it as white for default here. Okay. The artist can go back and change colors as they need and see fit, but you don't want to start out as a color because again it will affect the artist doing the material shading. So that's really, really important. Man, that would just be annoying if they constantly go back and change that all the time. Prepare for spitballs. Alright, so VS capital O for out here as our return type here, and then we're going to have our main VS because this is our main vertex shader here. Open parentheses. Now this is parentheses and not a curly brace. This is open parentheses here. VS capital IN. Capital I here, lowercase n. So we're doing our vertex shader in, and then we're going to do a capital IN for our variable name, and then close parentheses, and then open curly brace because why we're starting a block of a function because we're doing a function, right? So we have to have open and closing curly braces for a function. You can see that here. Don't forget when you click on a curly brace here, you find matching, and same thing for parentheses and such, matching parts here, and that makes life so much easier. Okay, so VS out here, space, all caps out, semicolon here. So this does our vertex shader here. And then float for PO here equals, and this, what's PO? Okay, so P is our point on our surface, alright? And then you're like, oh, well, okay, we always just called it P before. Yeah, this is going to be P from object space coordinates versus world coordinates. So I'm doing PW for world here and PO for object space. Equals float for, and this is common, you'll see this throughout a lot of other shaders too. Open parentheses, IN, all caps, dot, position, comma, 1.0, close parentheses, semicolon here. And then we're going to do a float 3 here, space, PW here for point in the world space, equals multiply, and we're going to do it by the world coordinate system here. So world XF with a capital X there, comma, PO, which is going to be what? Our object coordinate system, yes. And since this is a matrix here, it does need to be a float 4. If you don't have float 4, this will not work. So you have to have it float 4 because our matrix is a 4x4, right? And if you remember back to your matrix videos for mathematics, you have to have a 4x4 matrix multiplied times a 4x1 vector matrix. Okay, so that's what we're doing here. Our vector here is acting as a vector matrix. Alright, close parentheses here, dot XYZ. So we're only replying with 3 float values here. So XYZ into our position world point here. Okay, awesome. So we're going to have float 3 here, next one here, and we're going to say in here. Now you can get away with saying in here. We're in for being normalized normal here. So I just left it as in right now, but you'll see me name it sometimes as in like this for part of my naming convention. And I may just do that right now because it's a nice convention for naming, so that way you know, hey, this has been normalized, or no, it hasn't, with a lowercase n thereafter. So we're going to normalize this, open parentheses here, MUL for multiply, and then what we're going to multiply, open parentheses, world ITX, or world inverse transpose matrix here, X, and then F here, comma, IN dot normal, so we're going to multiply that times our normal. And this gives us our normal in world coordinate space coordinates here. Close parentheses, dot XYZ, close parentheses to have it normalized and then returned back. So we end up with our normalized directional vector here for our normal, and it's in world space coordinates. Perfect, awesome, that's what we want. Semicolon, and this allows us to do the lighting easier, let's put it that way. Makes life easier if you just calculate everything from a world space coordinate system for the most part for these calculations. Alright, so here we got our diffuse here, and it's going to be our L. Now remember, our L is our vector going to our light for our light direction in which it's coming and hitting the surface. So the point at which the light is. So for instance, this is L. See how I'm moving this light around? The point on the surface to this light is our L. Okay, cool. You can see how the reason why we want this set up so that I can move the light around and it affects the surface, and the light follows according to the and the shading changes according to the position of the light. So that's why L matters. Okay, and of course we're doing L in for normalized L here. We're going to normalize our V2 for our viewer direction here, and what we're going to do here is we're going to float 3, and this gets into our specular area here now. VN here is going to be our normalized V or viewer, I, camera, whatever you want to say, direction vector, where it points back to the view, the camera, or your eye, depending on how you want to look at it. Camera from a CG programming standpoint, or view, if you want to call it that, because technically there is no camera in OpenGL. You're just moving the entire world through the screen, basically, to make it simulate like a camera, if you will. I'll explain that in more depth when we get into the OpenGL series. That's going to be kind of confusing for now. Really need to dive into the OpenGL programming part so you can really understand what's going on with the view frustum, perspective distortion view. Yeah, we'll leave that alone for now. Okay. Okay, so that gets normalized, and we're doing it by our inverse view matrix here. So, and we're going to do it for a very specific place. Now, if you remember your transpose matrix, has all right. So I'm going to load this up real quick. Okay, so remember your transpose matrix here. Well, it had a very special place for transforms here, for translation. So TX, TY, and TZ. We'll check that out. X, Y, Z, W. Yep, that's W position. And this first row here in the matrix is 0 in our array. So that means in order to access that, check it out. View IX here, which is our view inverse transform matrix. 0 here is going to be that first row, right? So that's the very first row here, and then the W is going to access what? Our TX, our translate X value in that matrix. And that's exactly what we're doing right here. And check it out. We're going to be accessing each one here. Each one's a W here for each row. And it's exactly what we're doing. We're hitting down TX, TY, TZ in a row like that, right? So the next row in the matrix will be 1, right? So that'd be that second row in the matrix, which is going to be this one here, and then W is going to be TY. So we're accessing TY there. That's what's going on. It might be confusing just looking at the code, but that's exactly what we're doing. And then we have our view IX here, and then 2 here, dot W. And again, that is our third row here in our matrix, and the W is going to be T, or translate Z. Awesome. And so basically we just grab those particular values straight out of that matrix and accessing it as if it was a vector. And we're subtracting that translate position here from our point in world space coordinates that's on our surface of our model here, in this case the vertex point on the model that we're shading here currently. And that's exactly what's going on with that. So after we do that subtraction there between these two, then we normalize it so that way we get none of the magnitude or the length or distance of the vector, if you will, and we end up with just the direction of it, and that gives us V. In this case I said VN because it's been normalized, and I did LN over here, so it's normalized also. And we need to calculate RM. So RM is going to be, I'll call it RN. I've been calling it RM for a while now, but I like N here to let me know that, hey, R has been normalized. So it's just a nice way of keeping track of when you have these little N's here or not, whether or not something's been normalized. So I'm going to do my normalized L vector, which is what? My vector to my light, right? From the point to the light, plus the vector going from there to the view, for my view here. And then I'm going to add those together, and then they're going to be normalized because why? Because these two normalized vectors add together will end up with a vector larger than 1, for each area overall magnitude of the vector. So we need to normalize it again. So that way we end up with just the direction of these two vectors added together for r, and none of the magnitude of that mathematical operation by adding them together. Awesome. So that gives us Rn here. Great. Lit v here. Well, lit v is just a variable we have as a lit vector, if you will. And we're using the lit function, which I'm getting ready to go over here in just 1 second. This is a really important, really awesome function here that's in the reference material, in the reference manual for CG Shader Programming 3.0. Let's go ahead and save that real quick. Awesome. And so that'll be calculated. Okay, so let's talk about the lit function here. Alright, so this function matters, it's very important, and we definitely need to have a good understanding of it. So if we go over here to our CG reference manual, and like I said, this is an excellent reference manual. It's not something we try to learn from, but it is really good for looking up stuff, information when you need to know particulars of something. And you can't memorize 1,137 pages in your head of information and to recall it off for the slightest semicolon here, comma here, this particular order for this particular set of variables, blah blah blah, whatever. Maybe that's a little fuzzy from time to time, so it's really nice to be able to come back here and just pull it up easily in this. On page 774 in the PDF manual, you will find the lit function. Now the way we're using it is like this here. We're doing float 4 here, and it's because it's going to return a float 4 here. And it's going to be, the name of the function is lit, and it basically helps us do our light algorithm calculations. And it's faster and more efficient to do it with this function because it makes good use of the 3D hardware on the 3D card. So, best off using this. We didn't use it in Lambert because it returns several values that would not be used and cause for extra calculation. So it's very useful once you hit Phong and up for all the other lighting models. Pretty much we'll make use of this particular function, but for Lambert we just didn't have enough going on to where it could make good sense to use this, so I didn't. Okay, so here we have float here, space n.l, so we're going to do the dot product of our normal and our light vector here, and both of these have been normalized ahead of time. They'll be passed in. Do not pass in unnormalized vectors. If it's either one, if you do this on either one where it's not normalized, you're going to get terrible results. You may not even get light. You might not even get color, even when you change color on the shading, because it may be so screwed up from the magnitude of these two vectors being dotted with each other. So again, make sure these are normalized vectors that are being dotted together. And then we're going to do the float, and this is going to give us our diffuse color here calculation. This is going to be for the, guess what? Yes, that's right, specular. So float here n.h or n.r in our case. R is more typical. Sometimes they'll refer to h as the half angle between the two spaces in the place of calling it r for the reflection angle. But anyhow, float n.h, comma here, and that lets us do the dot product of both the normalized n and the normalized h. So let's not forget that. Float m here. M is going to be our shininess, magnitude of our shininess. So that goes into that shininess artist-driven parameter we had in the interface to get placed in here for m. Close parentheses, semicolon. Alright, awesome. And that's what we're most interested in. Alright, so I just explained what all this was here. Alright, great. I always do that. I forget how sensitive this thing is. Alright. Okay. So here's our description. Right down here. Alright. Very careful about my scrolling here. Alright. So we have our x. So the x value in our vector, because remember this is a float 4 and it's getting returned here. So the x value that's going to get returned is going to be our ambient coefficient. And it's always between 0 and 1. Oh, sorry, that is always 1. Sorry, it's always 1 here. So you don't have to use it if you don't want to. It just comes back as 1. W also always comes back as 1, so who cares? So the only two values we're really interested in are going to be y and z here. Your y1 is going to be your diffuse coefficient, that is 0 here, if n.l is less than 0 and n.l otherwise. So If you dot your N with your L here, then you can have your diffuse coefficient being done here. So it's maximum here. Sorry, the maximum is your N dot L, and then your least would be the 0. But you know, if at any point in time the coefficient that is 0, if N dot L is less than 0, then you know, basically, okay, let me put it this way. If N dot L is less than 0, then it's going to replace that value with 0. And so the lowest it can possibly go is 0. That's the best way to say that. Alright, moving on. A specular coefficient, that is 0 if either N dot L or N dot H are less than 0. So basically, if N dot L for your diffuse is less than 0, or your N dot H for your specular is less than 0, if either one is less than 0, then it's going to reply with 0. Otherwise, N dot H raised to the power of M is going to be the value that's going to be returned. Okay. And that's exactly how it works. Okay, very cool. And it gives us some nice results. Alright. Now, I put in here just to show you, but it will not change it or make it a difference at all. Well, okay, let's talk about this first. So here I am. I'm doing the dot product of my LN here. Remember, my light vector here, normalize, by my normal vector, normalize, and then by the dot product of my RN, or my reflection vector, normalize, by my normal that's normalized here, and then to the magnitude of to the power of the specular power here, that's artist-driven control here, this particular control here. Remember, we have the slider here, so you can see that in action. Okay, cool. Alright, and so then again it replies with all those values. Remember, x lit v here doesn't make any difference, so technically I could remove this if I like and not have it in the calculation. And actually, you're better off if you do, because that's one less thing you have to multiply. Therefore, that's one less calculation that has to be done on the 3D card, which means it's going to run what? Faster. Yes, it will run faster if I don't do that. Awesome. And then here we have our diffuse equals lit v dot y times lamp 0 color dot RGB semicolon here. So this is going to be what our light color times the diffuse coefficient here, or our diffuse intensity of the point. So for instance, let me point this out then. My diffuse intensity point here on the surface over here where my cursor is pretty low. It's almost black there, okay? Whereas it's going to be, so it means it's going to be pretty close to 0, right? But if I'm over here, more in the direction of the light itself, it's going to be pretty high. It might be 1 even, as far as that goes for intensity. So depending on the angle of the point on the surface from the light, or whatever, it depends on the intensity it gets for that point on the surface. So, and of course this is being calculated across all the points simultaneously. Awesome. For all the lights, if we set that up. Okay, so with that said and done, let's move on. So that gives us our diffuse here. And don't forget, KA is our ambient color control here. I just did a .rgb, although technically I wouldn't have to. I could leave this off if I wanted to. Times global ambient .rgb. I just put that RGB in there so you know that, oh, this is color that we're doing. Yes, it's color. Semicolon here. And remember, our global ambient is our ambient shadow here. And that gives us our overall ambient value. Here's the float 3. I already talked about the overall diffuse value here, float 3. And now let's do our specular. Alright, in the case that we're doing our specular, I'm taking the diffuse coefficient times the specular coefficient times the ks.rgb coefficient, which is going to be our ks color, shall I say, or our specular color, which is this control here, times the lamp color, which is going to be what? The color of the light. All that multiplied together gives me my specular color and my specular highlight here on the surface. Okay, so with that, moving forward a little bit more, out.color equals float4 here, open parentheses, specular, plus kd.rgb times. So we're doing our kd value here for our diffuse color, and I'm multiplying it times diffuse plus ambient added together, and then the final RGB value returned from that being multiplied across there for that part here. So, and then to the 1.0, sorry, not to the 1.0, 1.0 for W. Okay, so let me say it one more time. We're multiplying our KD here, our diffuse color, times our diffuse coefficient, or our diffuse intensity, shall we say, plus our ambient intensity color, if you would say, on there. Alright, so these get added together first, and then we're multiplying this. After that, we add it to the specular. After that, we determine that it is .RGB being returned and not, RGBA. And then we add the 1.0 on it in order to get RGBA here for the color. Okay, now we're going to do the position out. So we got our color for our different points on our surface. And now let's do the position. And again, we're not using a pixel shader at all. We're doing this purely with vertex shading altogether. So here we are, just doing this purely with vertex shading. Out.position equals mul for multiply MUL, open parentheses, world view projection, because it's a world view projection matrix here, comma, float 4 here, and then I got dot position. Now honestly, I can make this a little easier because I did that variable up above, which was our PO for our object. We've already done this right here, so I can replace this safely with PO like that, and then close parentheses, semicolon, and it just makes it just a little cleaner and easier to read now. Then we're going to return our out here, all caps here, semicolon for our struct, and then close curly brace. And I'll go ahead and save real quick and rebuild to prove that it does work indeed for doing that PO like that. And so you can see here, no problems whatsoever. It worked perfectly. So yes, you can do that, and it does make it a little cleaner and easier. I guess I'm just like, tweaking things as I go. Alright. So with that, I like having double spaces here between my technique and the other part. Technique 0 because it's the first technique. Pass P0 here because it's the first pass. I am doing open curly brace here. Open curly brace because these are blocks of code. Alright, so we're going to do our depth test enabled equals true, just as always for the longest time now. Semicolon, depth mask equals true, semicolon, cold face enabled equals false, semicolon, blend enabled equals false, semicolon, depth func equals less than or equal to, or L equal, semicolon, and then we're doing our vertex program equals compile space VP40 main DS open close parentheses semicolon. And you can test other profiles too. Would another profile build on this, like 20 for instance? And the answer is yes, 20 would. And technically, if I was doing this for production, I would leave it at 20 because that means 20 will work, and along with everything else above it. So hey, that's great. And I don't have to sit there and program out as many different shaders as possible because I can have without no worry about fallback and all this stuff. This would make the shader run on more hardware, obviously. But with that covers Vertex Phong lighting for the Vertex shader without texture influence. This is just purely for the color. Alright, in the next part here, we're going to go ahead and do the Vertex shader with texture applied to each part here, and R is controllable. Alright, that was PhongVertex shader, and we're going to move on now to the PhongVertex texture shader. But with that, my name is Nate Nestler, and this is Hyperactive Studios. Thank you very much.